Excuse me. All right, so what we have is, yesterday we talked about what happens to things when you heat them. And I'll use my hands here a little bit. So let's say you had anything, a piece of steel, a piece of water, a balloon full of air, and you heat it. What happens if you heat something? What happens to its mass? So let's say you're going to make it hotter. What happens to the mass? Becca, what do you think? What happens to the mass of an object if you heat it? It does. Very good. Now, let's see. Nate, what happens to the volume of items when you heat them?
Volume of what?
What now?
Volume of what?
It could be water, steel, air.
When you heat it up,
So I'll give you a hint. When you heat it up, the particles move a little faster, and they move each other a little bit further away. Expands, right? So it actually gets bigger. By the way, a solid and a liquid will just get a little bit bigger, but a gas will change its volume tremendously when you heat it. And then next question is, what happens to the density? So let's talk to Ella. Ella, can you do it? So we know what happens to mass. It stays the same. Nate says the volume increases. So what happens to the density if you heat things up? Yes. Now, again, solids and liquids will be a little less dense, a little bit, and gases can be really a lot less dense. All right, so anyway, we got into that, a little bit of conversation about that, and we saw this paper, and I'm giving a tiny grade for this, even though we're going to kind of do it in class. Anyways, for this one, we said, what is the equation for linear expansion? And so here's a fancy looking equation, and we said, what do each of these letters mean? And we found out that delta L means the change in the length. Yes? Oh, you're right. You're right. I had it on pause. Okay. All right. Oops. All right, thank you. Thank you. So this means it'll change. How much will the length change? And then this right here, if I was an engineer, I would have a whole chart, a whole book of these, and it'd be called the coefficient of linear expansion. Now, you don't have to know that. I would give that to you. And I would give it. So this one, it says steel expands in 1 part per 100,000. So I'm going to use the number 1 over 100,000. So that's just a number I'll give you. So delta L equals how much it expands per whatever. And then times, what's L sub 0? What do physics people like to use that 0 for? Do you know? Yeah.
The original.
The original. Sometimes they use I. What's that mean? L sub I. Initial. So it looks like a physics thing, but it really just means the original length, and then times delta T. So we found out that if you took 1,000 millimeter piece of steel, and you're going to heat it and make the temperature go up by 10 degrees. Be careful. How much longer is it going to get? And it was a whopping, how much? 1/10 of a millimeter. Now, here's a millimeter, 1/10 of a millimeter. You say, why are we even studying this? It only increases by 1/10 of a millimeter. You're right. With small amounts of material, you won't have to worry about it too much. Now, if I worked with something like electronics or something that's really small anyway, though, would that little increase might make a difference in my engineering? When I try to engineer something, I'd have to make sure I watch out for expansion and contraction there. So the next question they ask, well, then how much longer would 1,000 meter? So what kind of piece of steel is 1,000 meters long? I've been on bridges that go over water, and they're like more than a mile long. That's 1.6 kilometers. That's 1,600, and it's a piece of steel covered with concrete. And so what happens there, if you raise it by only 10 degrees, it'll get about this much longer. And you better engineer for that. If you don't engineer some kind of an expansion area for that expansion to occur, it will expand by buckling your bridge. It'll buckle. So all engineers know about contraction and linear expansion and contraction. Then we went down here and we found out the Eiffel Tower, between summer and winter, there's about a 30-degree difference in temperature. Will be about this much higher in the summer and about that much shorter in the winter. The next thing we did in class is I thought it was intuitive that if you had a ring, and I had on the video yesterday, I had a little metal ring, and a ball barely fit through the ring. And what I did was I heated the ring, and what do you think would happen? I think the ring would expand, but what about the center hole? Wouldn't it expand and close the hole? And I would have thought that for sure. We actually did it, and the hole was bigger. And so I think what the author did here was pretty smart. He said, think of this kind of like a ring, but I'll leave a gap here so we can study two things at once. See the length, see the width? Just make it longer and wider. Make each box longer and wider and let it expand. And if you redraw it, you'll find out that the middle circle is bigger and the gap is also bigger. See that? Anyway, so that kind of, now I understand why the circle would actually get bigger, not smaller. And another one, I told people they could go home and do this one. This one's where you find the original circumference of a pipe. Here's a pipe that's snug on the earth, and so it has a certain radius. It tells you what the radius is, R1. And then everybody in the world is going to breathe on it, and all I want to do is make the temperature of that pipe increase by 1 Celsius degree. How much bigger will the pipe be? Will it be this far above the ground now because it expanded this far? And if you do the math on here, the new pipe will be bigger. Oops. The new pipe will be bigger, the expanded pipe, and the radius will be bigger, right? Let's call that R2. So R2 minus R1 will tell you how high off the ground it's going to be. And the good news, they have that same problem here on page, if you like math, so we can find the page. Yeah, there it is on, nope. Nope. I lost it. It's on page 418. So if you want to go to page 418, it actually tells you the answer. Yes?
For the test, should we memorize that equation, or are you going to give it to us?
Which one?
The one in the top corner.
At the top?
Yeah.
I'll give it to you. Yeah, I'll give it to you. Now, so what happens is, believe it or not, by raising the temperature of that pipe 1 degree, just one, it would be a whopping 63 meters up in the air. 63 meters 6 up. That's how much bigger that pipe will be by raising it by 1 degree. And we had some good questions yesterday. I don't know enough about space engineering. I don't know enough about that. But you would have to be careful about that. If you engineer something on Earth and you take it up into space and everything starts contracting, they would have to be careful about that. The space shuttle had, mainly it was painted white. And if they made that part face toward the sun, they wouldn't heat up very much. But you have to be careful because if you wanted to heat it up, you might paint the shuttle some other color. And say, I'll paint it some other color like dark, and then I'll use it to heat my cabin up with. Now, the next thing we did yesterday is I'm gonna do something a little different because oh shoot, I already have the answers here. So, hey Ryan, can you do me a favor? Can you do me again? I have one. Never mind, I got one here. Thanks. Let's flip this over, and even though you can do this page mathematically, I would like to do this page conceptually. No math, okay? Here we have, it says I have 1 liter of water, and I'm going to heat it until the temperature goes up by 10 Celsius degrees. Now, the question says, let's say it takes 15 minutes. Then I'm going to heat 2 liters of water for 15 minutes. I'm going to add the exact same amount of heat. What do you think the temperature will be? And tell me if that's intuitive to you. Is that intuitive to you? What's going to happen? I'm going to add heat to that, and guess what the particles are going to do? Hey, I'll take that heat and move around faster, and the thermometer goes up and up and up. The thermometer tells me what's happening to your average kinetic energy. So now, what if I do the same amount of heat and 2 liters of water? What do you think? David, what do you think?
Can you say it again?
Okay. It again. Oh, you mean the question? Okay. So if you had $1 million and you gave it to 1 million people, each person would get $1. But if you had $1 million and you gave it to 2 million people, how much would they get? They get half, wouldn't they? So if you get a certain amount of heat and it heats this many particles and makes them increase their kinetic energy up to 10 degrees higher, what would happen if I gave the same amount of heat in 2 liters of water? I think so. Is that intuitive to you? And what about, Dave, what about 3 liters of water?
It would be like 3.3.
Yeah, I like to see. So it's kind of intuitive, I like that. Now, the next set of questions are also easy, but then the last is where you have to be careful. It says here, a large bucket contains 1 liter of 20-degree water. What will the temperature of the mixture be if I pour a liter of 20-degree water into that? So if I have another liter of water at 20 degrees and I pour it in that, everybody in the room who's alive will know the answer to this one. All right? All right, Ryan, what do you think?
20.
That was easy, wasn't it? Say with me, Ryan. Here we go. What will the temperature of the mixture be if I have 1 liter of 40-degree water and I mix it with 1 liter of 20-degree water? All right. And the last one, if 2 liters of 40-degree water were added, would the temperature be greater or less than 30? Okay, pretty easy, huh? Is that pretty easy? Because 2 of the 3 liters that are in that mixture were at 40 degrees, weren't they? So it can't be halfway. It's got to be a little bit closer to that. And there is a mathematical way to figure out what the temperature would be. And we'll use that equation. We used it yesterday. We'll use it again today. Now, let's go down here. This one is a little bit harder. 1 liter of water, and you're going to put in a kilogram of red hot. It's going to be red hot iron. Okay. Now, here's what's going to happen. Which way does heat always travel? Not fair. I can ask you, Mason. I think. Which way does heat travel? You say, what do you mean? Which way? You mean up, down, left, right, or what was it? How would you say? Yes, it always travels from hotter areas into areas that are cooler. So, ready? Higher temperature to lower temperature. Now, so what's going to happen here? I put this really, really hot piece of metal in the water. Is the metal going to gain heat or lose heat? Everybody got that? And the water is going to gain heat. So let me ask you this question, Maggie. Which one's greater, the amount of heat lost by the metal or the amount of heat gained by the water? And that's a really big concept in this chapter. Which one's greater, the heat lost by the metal or the heat gained by the water? So that's a little bit harder question. What do you think? Want to take a guess? Which one's greater? This metal is going to lose heat, and the water is going to gain heat. Which one's going to be greater? The amount of heat lost by the metal or the heat gained by the water? Just think about it like what comes to mind intuitively. Let's say, okay, let me, let's see. Ian, what do you think? Yet again? What?
For A? Or is it for
No, just in general. Which one's going to be greater? Well, we can do, actually, let's do B. The quantity of heat gained by the water is equal to the quantity of heat lost by the iron. Is that true or false?
True.
True. That's always true. Now, that's again, that's assuming that the container didn't, gain any heat like that. So one thing you got to be careful about is this is always true. Heat gained by one object has to be heat lost by another. When you shake somebody's hand, we haven't done that for about a year, but anyway, I do it still. But you shake somebody's hand and you say, well, their hand feels kind of warm. You know what they're feeling? If their hand feels kind of warm to you, guess what they're feeling? Your hand feels kind of cold to them. Every time I do that, I always think, what if your hand feels cold to them? All right, there you go. So let's look at the next one. Look at C. Here's another big idea in this chapter. Yes, go ahead. Oh, you're ready to answer it?
I said true.
Okay, it says here the iron and the water will both reach the same temperature. That's a big, big true. These are big truths. Now, how do I know that? Because what if this piece of metal was hotter than the water right next to it? What if the metal was hotter than the water right next to it? What would happen? What happens anytime you put a hot and a cold object next to each other?
Heat transfer.
Heat transfer, and then eventually everybody will be the same, wouldn't they? They have to reach the same temperature. Now, here's the hard questions. Here's the hard. A, the increase in water temperature is equal to the decrease in the iron's temperature. Boy, if I was a human, I am. If I were sitting there and I said, that sounds very much like what you said here. And it's so compelling to put true here, but it's a big, big false. Anybody want to help me on that one? Why is this a big, big false here? All right, Owen, what do you think?
Well, if you account for specific heat and the capacity factor, water has a larger one than iron.
And so, that's exactly right. Look over here. If you weren't here yesterday, here, just so you saw in the video, we looked at this chart, and it's called specific heat. And specific heat says how many calories of energy do you have to either gain or lose per gram to change it by 1 degree Celsius. And what I asked him to look at yesterday is, what does it mean to have a really tiny specific heat? And you did a good job on that, Owen. It only takes a little bit of heat gain, and your temperature will shoot up a degree, a little bit. Or if you lose a little bit of heat, your temperature will drop very quickly. Get that? But we'll look at water. Water has one of the highest by far, one of the highest specific heats of anything. What does that mean? It means it can absorb a huge amount of energy and maybe only change a little bit in temperature. You know what's good about that? It can also release a huge amount of energy and not change its temperature very much either. So when we see that, we'll do that problem here in just a minute. We'll do it again. We didn't finish it yesterday. So you're right. The heat gained, the heat lost by the metal is X amount. Let's say it lost this much heat, ready? That much heat will change the temperature of the iron a huge, huge amount because it has a low specific heat. But that same amount of heat that's gained by the water has a high specific heat, it only raised the temperature a little bit. So there's no way the temperatures, yes, the temperature will end up being the same temperature, but the change in temperature, the thing with the smallest specific heat will always change a temperature greater than the other guy. And the last one, the final temperature of the iron and water is about halfway between. I don't think so. If you had metal that started at about 100, let's say it got cooled down to, I'll just make up a number, 30. Let's say you had water at 20 and it went up to 30. That might happen. This guy will change, I'll go all the way down to 30. This guy will go from 20 to 30. And is that halfway between 100 and 20? Is that no. There's no way. It's not going to be halfway. So that's a big old false there too. And the last one, when Queen Elizabeth throws her last sip of tea over the Queen Mary's rail, the ocean will get a little warmer. What do you think? What do you think? No? How many people say yes? True. Wow, that's called peer pressure. Oh, thank you. How many people say no? Oh man, that's called not all right. That's called apathy. Oh, sorry. Let's try it again. When Queen Elizabeth throws her last sip of tea over the Queen Mary's rail, that's an ocean liner, by the way, the ocean will get a little warmer. How many people say true? How many people say false? Okay, why would it not get warmer?
Because the last sip isn't going to have enough heat to raise it up a whole degree.
What now? Oh, no, wait, I haven't thought about that. I think I see what you're saying. She wouldn't throw it over if it was still hot.
No, the last.
He thinks you mean raise it by an entire degree.
Oh, no, I never said that. I never said that. And there's no way I'd be able to measure it, but in theory, it would actually raise the temperature by a little bit, wouldn't it? And certainly not a degree, not even a millionth of a degree, not even a billionth of a degree, but it would raise it theoretically a little bit. All right, so everybody on that? So if you weren't here and you want to take that home and finish it, I give a very, very small grade for that. And then the other homework you've been working on for almost 8-9 days, something like that. Now, here we go. Yes?
Crash area now.
You have it done now? Okay, on that back table, I make it stacked for the other class, and that's what they're doing.
Wait, do we turn it, does everyone turn it?
What now? Okay, now, here's where we were yesterday. Now, if you have a calculator, I'd like you to get a calculator out. If you'll get your calculator out. This problem here is almost identical to one that will be on the test tomorrow. And as a matter of fact, the person who wrote this, that's at least 8 years, 9 years, 10 years maybe ago. It's not like she was sitting around one day and said, I don't have anything to do. I think I'll make a physics calorimetry problem. No, that's not what she did. She didn't do very well on this part of the test. So for extra credit, she said, I'll make my own a practice question for that. And then students after me can do a practice one, and they'll be ready. So here's what we did. Take a look at it. It says a physics student has 100 grams of a metal that was heated to 100 degrees Celsius. Then the student drops the metal into a beaker containing 150 grams of water, and the initial temperature 20 degrees. The final temperature of the metal and the water are both 25.46. All right, so here's what we do. If you've been gone twice, maybe once for sure, you would not have seen this equation. This is one of the biggest equations in the chapter, and it says heat gained or heat lost. If you want to calculate heat gain or heat loss, that's what Q is. I wouldn't use Q. I would use H, but they use Q. So I'll just say quantity. I hereby declare I'm making it up. Q means quantity of heat. There you go. If you want to gain heat, use this equation. If you lose heat, use this equation. And Q equals MC delta T. MC delta T. What's M? M is mass. This is called a specific heat constant. I will give that to you. I will give that to you on a chart. Get that? It's a constant. If you're an engineer, you'd have a whole page and page and pages of these. Next, delta T. How much did your temperature change? So what we're going to do here is, this is where you have to focus your mind a little bit. What's going to lose heat and who's going to gain heat? I got this piece of metal. I put it in boiling water. I leave it there for a long time, and the water's 100, so the metal must be 100. I got this little insulated cup, and it has 150 grams of water in it, and it's at room temperature at 20 degrees. And I say, are you ready? Ready? I take some tongs, pull the hot metal out, put it in there, put a lid on it. That's called a calorimeter. I'm going to try to measure heat gain and heat loss. I'll show you I'll show you a regular calorimeter. It's between $19,000 and $29,000 if you want to buy one. I used to do a lab with this where I used Starbucks cups. It still gave you like 30% error, maybe 40. You could never get a really good number because it's just too much. It's not that great. So here's what we're going to do. How much heat was gained by the water? And you say, wait, there's an equation for that, isn't there? Yeah, MC delta T. What's the mass of the water? Go up here. What's the mass of the water? I found you. 150 grams. For those of you, and I'm not going to call your name out, who don't like to use units, all right, if you don't like to use units, you're going to get hurt on this because look at this chart here. I have specific heat in grams, calories per gram Celsius degree, or joules per gram Celsius degree. If I asked you to figure this in joules, you'd have to use this one, wouldn't you? If I say in calories, you would use this one. So anyway, here's that. Here's the specific heat of water, which is an easy number to remember. 1 calorie, and I'll give it to you, per gram Celsius degree. And what's the delta T? All right, here we go. What's delta T for the water? How do you find delta T for anything? How do you find delta anything? Isn't it the second value minus the first value? So the water ended up at 25.46. It started at 20. So what is delta T for the water? All right, here we go. Now we're ready. So now we have everything we need. And if you put that in a calculator, we should be able to find the amount of heat that's gained. Heat gained by the water. Let's put that in there and tell me what you get. I'll give you a little clue here. This cancels, 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 cancels. And it's going to be in calories. All right. Do you have a calculator? Everybody calculate this and tell me what you got. I know what the other class got, but you guys haven't done this yet. How many calories of heat energy were gained by the water? Sophia, do you have it done yet? Punch it in. Nice, 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 nice. About 819 calories of heat were gained by the water. Now the next problem, and I'm not trying to fool you, but the next problem is how much of the specific heat of the metal, how in the world am I supposed to know that? Well, I'll give you a clue. MC delta T for the metal. And so here's my problem. I want you to find the specific heat of the metal. I better give you this. I better be able to give you that. I better give you that. And I better give you that. So let's see how many of these you can find. What's the mass of the metal? Ooh, I see it. I see it. I see it. What? Oh, we don't know that. They want you to find that. So I'll put that down. Fine. That's my X. What's delta T for the metal? Well, the metal, its final temperature was 25.46. What was the initial temperature of the water, of the metal? I'm sorry. 100. So what's delta T for the metal? What's that, 74.54? Is that right? All right, so now I got my number. All right, 75.4. All right, and wait a minute. We can't solve for two unknowns, and I had to find that, so where's that number come from? How am I supposed to know that? Rollins, how do they have want me to find that, so they had to give this to me. What is this number? What is it? How much? Calories, right? And that's a big idea in this chapter, isn't it? The heat the heat gained by the water, see that? Has to equal what? The heat gained by the metal. Now I have this number, and this one, I should be able to solve for that. Since I said something funny? No? I said something wrong, right? No? So now, you guys are such high-level math people, you should know that you would take this number here, divided by that, divided by that. You know how you do it? Let's do it. Take that number there, divide by that, and tell me the specific heat of this metal. And who have I not called on yet? Hey, Clayton, done. That's a little fast. Maybe that's too fast for you. How do you solve for that? And if I'm going too fast for you, I'm sorry. Do you have a calculator with you?
Yes.
Okay. This divided by that, divided by that. What do you got? What is it? 109. Okay. Even though that's really close, the other class got something else. Did anybody else get something different? Anybody else get 0.111? What'd you get? Oh, no calculator? What'd you get? 1 1 what? 110. Okay, I got you. Okay. So now, you know what the calculator can't tell you is the units. What are the units of this thing? It was calories per gram per. That looks like specific heat units, doesn't it? And now we go over here. Ooh, here's the good part. Look, What's the metal? What is this metal? Look, aha! Like I found you. Iron. And by the way, on this one, all you have to do is put 819 calories, and you don't have to show your work because guess what? Heat lost by the metal equals heat gained by the water. We figured out how much heat was gained by the water. That's how much heat was lost by the metal. What do you think? So the back page tomorrow on the test, that's when it's going to look like this. I changed the numbers a little bit. Get that? Now, you know, every year we've given this test, I have about 3 students out of maybe 30, 40, 35. 3 students will come to me later because they mess it up. They mess up this page, and because here's what the test might look like. It'll say blah, 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 and it'll say this. The final temperature of the metal is 25.46. And then they act like they can't finish the problem because what are they going to say? I'll say the final temperature of the metal is 25.46. And they say, well, I can't finish the problem because I don't know the final temperature of the water. That's why I couldn't do it. Well, I'll listen to your complaining, but it is complaining. What am I assuming they should have known? It's a big, big idea. It's a big idea in this chapter. And they're saying, I didn't tell them the final temperature of the water. Yes or no? Did I or not? I did. If the final temperature of the metal was 25.46, what's the final temperature of the water? It has to be the same, doesn't it? How could you have a piece of metal at one temperature and water at another temperature, and that be the final temperature? It would never happen. It would never happen. They have to have the same final temperature, don't they? I keep looking at your face. I can't tell if that's yes, no. Okay, that's a big idea in this chapter. Heat gained equals heat lost, yes. And final temperature of both are going to be the same, yes. And here's where you're going to get tricked tomorrow. I don't want you to get tricked. The change in temperature of both is the same? What do you think? That look the same to you? The change in temperature of the iron is the same as the change in the temperature of the water? No way. Not even close, is it? All right, well, I hope that makes sense to you. Yes?
If there was a very small amount of water and a very large amount of iron, could the change in temperature be the same?
Could you what? If I got the first
If
part.
you had a small amount of water and a large amount of iron, could the change in temperature between the two be the same?
The last part, could you change the temperature what?
If you have a small
I got that.
could you have an equal change in temperature?
Oh, yes. If you were to do some calculations, you could figure out the exact amount of water, a little tiny bit of water and a lot of metal. You could actually, that'd be neat. That's pretty neat. I like your thinking. I like your thinking like that. That's true. All right, you okay? All right, so what I'm gonna do is I'm gonna do the talk about the last part of the chapter, and then we might have a little bit of time to review a little bit. I'm going to go to, and this is that's all the math there, and let's go to water, okay? Certainly, if you think about water, it's a little tiny guy, and yet it has so many things that are unique. It's almost like if we go to heaven, you ask God about water, say, oh yeah, I did that on purpose. Because it's such a special molecule. It's tiny, but it has such unique qualities that other things don't have, and it actually makes the world. It actually makes the world that we have here. Here's one, for example. When you go to the beach this summer, you get up early in the morning, okay? And let's say that it's about 10 o'clock in the morning. That's not early, but 10 o'clock in the morning, and if you stand there and face the ocean, you'll feel air coming toward your face. Now, I'm not trying to talk about storm systems or things like that. Every morning, if there's no real wind, you can stand on the beach and feel a wind coming to your face. And what happens here is sand heats up faster than water. Low specific heat, high. So guess what happens? The temperature of the sand gets higher than the water, and so the air above the sand starts rising. Well, you can't have a vacuum, so what happens to all that air? Who replaces all that air when the air rises across the beach? The air from the ocean comes in. You feel a little breeze. What happens when the sun is setting? The sand, who heated up faster, will also cool off faster. And now the warmer air is above the ocean, and it's rising, and the air from the beach goes out. So in the morning you feel, see, a breeze at your face. At night you feel a breeze going out toward the ocean. And that has to do with specific heat of water and sand. That's kind of neat. Now what I want to do, I'm going to show you this right here. Now, every item I know of, pretty much every object I know of except for water, here's what happens. If you heat it, the volume gets a little bit bigger and it gets a little less dense, a little less dense, a little less dense. If you cool it, it gets a little more dense, a little more dense, a little more dense. Get that? Everybody does that. Even water does it. Even water does it. See, like, here's the volume. It's incredibly small changes. Cool it, it gets a little more dense, a little more dense, a little more dense, a little more dense. And you know what? When it gets to 4 degrees, it starts acting different than any other item I know of. It should, at 3 degrees, get more dense, more dense. It should, every other item does this. It just gets more and more dense. Water does this really weird thing between 4 degrees Celsius and 0. It actually gets not less dense, but more dense. I'm sorry, not get more dense, it gets less dense, sorry. What in the world's going on here? For example, if I took gasoline and I froze it, and I put it in a bucket of regular gasoline, the frozen gasoline would sink. It's more dense. If I took a hot steel and I put solid steel in liquid steel, it would sink. Everything I know of sinks in its own liquid. But what does water do? What does ice do when you put it in a glass of water? It floats. What's that? It actually is less dense. And that's kind of strange, isn't it? And yet it sets up a really, really neat situation. And so let's take you back to 10th grade. Water, HHO, ready? Non-metal, non-metal, non-metal. What kind of bond forms between them? Covalent. They share electrons. One of mine, one of yours. That's a pair. We're going to share that pair. I'm going to share over here. I'm going to share 2 pair of electrons. But they don't share evenly. The fancy word is electronegativity. Oxygen is more electronegative, which means when we share the electrons, I'm going to make them spend more time around me than you. Oh, yeah? Well, that'll make the oxygen end of water slightly negatively charged. It'll make the hydrogen end slightly positively charged. And that's when you use the word, it's a polar molecule, it has opposite ends. So what? So what? Well, when you cool water and it gets down to 4 degrees, that's about 39 degrees Fahrenheit. If you get to about 4 degree Celsius water, the liquid water is as close, the particles as close as they will ever come to each other as a liquid. What do you mean? Go down to 3, they'll get closer. No, they don't. Everybody else does, but not water. Why? The plus and minus nature starts kicking in and starts pushing them around. And at this end here, for example, the plus end, the negative end of water, the oxygen end, starts being attracted to here, and then positive, push away positive. Which one of these looks more dense? This is ice. This is water at 4 degrees. Which one looks more compact? This one. Water at 4 degrees Celsius is the most compact liquid water we'll ever get. And when it gets close enough, when it gets down and get closer, they start pushing each other into this open hexagon. Wow. And look at all the empty space. And water is actually, ice is less dense than the water that it came from. That's very unusual. What I always think neat is what happens when you freeze water, water vapor, for example. If you freeze water vapor, it's a snowflake. If you freeze water droplets, it's called sleet or hail. But if you have a snowflake, what do all snowflakes have in common? They're all different slightly by little tiny things like this, but what do they all have in common? the six-sided. And I just think there's some beauty there. There's some beauty there that at the molecular level, open-sided hexagons, and at the snowflake level, the macro level, six-sided hexagons. And I want to show you the last thing I want to do for a review. Here's why that makes all the difference in the world. Okay, so we have water all over the planet. Sometimes the water is in big things like oceans. Sometimes it's in lakes, kind of deep. Some of them are in shallow ponds. One of the questions on the test will say, in the year 1900, on January the 1st, at the bottom of Lake Superior, what was the temperature of the water? You say, I always thought you were unfair. No. But what is the temperature? What was the temperature? By the way, Lake Superior is one of the Great Lakes, and it's up there. And I can tell you, I promise you, on January 1st, it's cold. It's cold everywhere. But what's the temperature of the water at the bottom of Lake Superior? 4 degrees Celsius. So let me tell you a story how that works, okay? Let's say you have a not so deep pond. Let's say it's, 20 feet deep, okay? And the pond was just being a nice pond in the fall, and all the water was about somewhere close to 20 degrees. And then all of a sudden, this great big cold air mass from Canada comes down. It sits on Greensboro for about 10 days in a row. Oh, it's really cold air. It's like minus 10 degrees Celsius, all right? So what happens to the 20 degree water when you have minus 10 air on top of it? Which way is heat going to travel? Is heat going to go from the air into the water or the water into the air? Everybody in here knows. Everybody should know this. There's 20 degree water, minus 10 degree air. Let's see. Avery, what do you think? Which way is the heat going to go? From the water into the air or air into the water? You're right, because it always travels from the hotter thing to a colder thing. Now, the air mass is so huge, you are going to warm the air up a little bit, but it'll dissipate, and the air will still be really, really cold. But this water is going to start going down to 15 degrees, and maybe 10 degrees, and then 8, and then down to 4. And what happens when it's 4 degrees? When it's 4 degrees, it's more dense than any water anywhere. So where does it go? Boom, goes to the bottom. Now the next air has been chilled, but now it's at 15 degrees, and it goes down to 4, and it goes boom, and boom, boom, boom. This whole pond has to be at 4 degrees before special things happen. Now this last layer of water, so you got a whole bunch of 4 degree water here, and you got this last layer of water, and it's at like 10. And it goes down to 4. He says, now it's my turn to sink. And everybody says, where do you think you're going? We're 4 degree, you're at a 4 degree. You can't go down anywhere. You got to stay up on top. They said, what do you mean I stay on top? Yeah, you're staying on top. Yeah, but. 3, 2, 1, 0, ice. See that? Now ice can form. And you say, what's good about that? Good about that, here's number 1. Ice will form a cap here and kind of insulate this water a little bit. And there's liquid water here. There are a lot of animals that can withstand 4 degree water all winter. They can handle it. They're not going to die. 2, it's kind of translucent. Sunlight can still come in, warm them a little bit. Even the plants can undergo photosynthesis. That's neat. And this life in this pond can actually survive as long as this ice doesn't get to the point where it freezes solid. And if it's a really shallow, it's only 5 feet deep, and the cold air stays a long time. 0 degree ice, 4 degree water, it'll freeze from the top down. But as long as there's a little bit of liquid water down here, they might survive. And that's really neat because every animal can survive now. Yes.
Why is the bottom 4 degrees without number? Is it?
Well, if it was, let's say it was 8. Let's say the water at the bottom was 8, and then 4 degree water comes down and it's more dense, so it would push the 8 degree water up on top of it. So eventually more 4 degrees would come, and then so 4 degrees is the most dense liquid water ever gets. So it's actually more dense than 8 degree water. Yes.
Is the bottom of the lake
No. Let's say it started at 20 degrees, and the air cools it off down to 4. If the air cooled it off to 4, it's so dense it sinks because of density. Now you might say, why doesn't it go down lower than 4? Is that what you're asking?
I'm just saying, like, why it wouldn't be warmer?
Why wouldn't it what?
Why the Earth wouldn't warm it anymore?
Oh, there's no doubt. If I was at Yellowstone, underneath the ground of Yellowstone, all over the place for 100 miles around, has a big bubble of Earth's magma not that far away. And that water would not. That water would get heated by the Earth. I understand what you're saying. You're right. For a while, even the heat from the Earth would maybe keep this a little bit warmer. But eventually, if you get more and more water, 4 degrees, it'll take that heat away, and it won't be having more heat to add to it. That's a good question. That's a very good question. Yes?
So if you dropped an ice cube in water that was hot enough that it was less dense than the ice cube, would it sink? I mean, obviously it would melt quickly, but would it sink before it melted?
Okay. Yes. If I could put an ice cube and the density of that happened to be greater than the water, if I had water so hot that it was really not that dense, you're saying the ice cube is more dense than the hot water, yeah, it would tend to sink, and then it would melt. That's a good question too. Wow.
So does ice sink in known water?
I don't know what the temperature would be. I'd have to look up the density of water at different temperatures, and the density of ice is about I forget the number, 0.998 or something like 9.
Didn't you have that little graph on the last page? Would it have one there?
Where is it?
No, that's volume.
Yeah, that was volume, but I'd have to look up some numbers. I could give extra credit for that. Find the density of water at different temperatures and find the density of ice. And yeah, since you ask it, once you want to look it up?
Yeah.
If you don't want to. But if you give me a chart showing the density of water at different temperatures and then the density of ice, and then we would know what temperature of water could ice maybe even sink in. Even though you're right, it would be melting too, but it might sink and then melt. Well, I think this is pretty neat. If water acted like everybody else on the planet, here's what would happen. The water at the top would go to 0, and then it would be the most dense, and then the ice would go to the bottom. And this would fill with ice, and fill with ice, and fill with ice, and fill with ice, and every living thing in that water would be pushed to the top, and you'd hear about some celebration that some country said, everybody, come out of your houses. There's free fish on top of the ice. And they would cook it because they didn't want to go waste. And you hear about it, and then the next year, there'd be no fish. There'd be no fish in there. We don't hear about that. So anyway, I just think it's so neat to think about the special properties of water. In this chapter alone, you heard about a lot of properties of water. All right, I'm gonna stop now. What I'm gonna do, not stop, but I have in this packet, here's what I would do if I were you. I would, a student did this one year. Here it is. A student, they took the whole chapter and they kind of made a review. And so maybe if you want to just look at that as you go down through it and say, yeah, I know a lot about that. I know that. Oh, I don't know that. And then they also had some more big ideas. They put some big ideas down here. And so if all of that makes sense to you and you've been honestly doing your homework, if you did the homework on that chapter, all this should have come together, I'm hoping. Again, one more time, if you feel like you missed more and it wasn't really your fault, I can't go till Monday. That's too far. And you have a test anyway. But if you just come tomorrow, then you have to take the test tomorrow in class. If you let me know that you're going to be in the ARC that period and you want to take the test after school, just let me know. If you want to say, I'm going to be in the ARC and study, and I'll take the test Friday morning or Friday after school, just let me know. So I'll be flexible in that in regards. Yes?
If we were in a group doing our homework,
I wish I could hear you, sorry.
actually, never mind. I think, did we all do our homeworks individually, or did we do it on one paper? Yeah, we did it individually? Okay, never mind, sorry.
Okay. So is everybody okay on that? So anyway, I'm willing to be a little flexible as long as I know what you're going to do. Okay. You just try to make a decision and come see me if you can. All right. Well, thank you very much. Thank you.
I'll give you on Thursday.
Wait a minute. Wait a minute.
I'll take it after school Thursday.
Okay. So on Thursday, you're going to be in the ARC.
Yeah, and I'll take after school that same day.
On Thursday? Okay,
Yes.
Thursday after school. Okay, thank you.
I think I'm gonna take the test Friday. 'Cause
Okay.
I have my thesis tomorrow.
All right, and so you're going to go to the ARC during class? You want to do that? Okay,
Yeah.
so Maggie,
I did everything else once.
you're going to be in the ARC on Thursday, and there'll be other people in there, and then you're going to take it Friday when?
Probably in the morning, but I might be able to take
You
it.
have to give yourself, they're going to get 55 minutes, so if you get here at 7:15, you could leave at 10 after and still be,
Yeah, I could.
so if you say Friday morning, you got
I
to
could
get
do
here.
Friday morning, or I could do probably first period Friday.
Do you have, stay home?
No, I have, well, yeah, technically.
I have no permission to get you out of somebody's class, but a teacher can give you their permission.
Well, yeah, I know. I have team sports, which is majority.
Okay.
So they're all fine.
Well, you know what? So if you're telling me Friday at first period, is that what's going to do? I'll leave it open, okay? But you're going to take it on a Friday. If I don't see you in the morning and I don't see you in first period, then you have to take it Friday after school.
Okay, yeah, I can't take it first period. I have to go see a thesis, so I'll take it before school or after school.
Okay, so either before. Okay, I got it. What do you want to do?
Can I take it after school tomorrow?
Okay, so on Thursday, there at least 3 of you can go to the ARC and help each other study a little bit, and then you're going to take it Thursday after school. Okay, all right. Is that going to help you a little bit?
Yes.
Because you've been gone quite a bit. So, and the best thing you could do is talk about it. This whole conception of physics. The more you talk about it, the better. So if you're going to study, talk. Just let's talk, let's talk, let's talk, like that. Take that big page here of the big ideas. Let's talk about those.
Do you want us to turn in the homework when we take the test?
Yep. So whenever you take the test, you turn homework in.
Hi. I have a study hall Friday morning, and I can take the test then. If-
Okay. So do you want to be in the ARC tomorrow during class?
Sure.
Okay.
Yeah,
Yes?
that's good.
Okay. So right now, Thursday in the ARC, and you're going to take it when?
Friday
Friday,
morning.
First period?
Yes.
Okay.
first period.
Okay. I hope it helps you out.
Yeah. Actually, I guess I could get here early so I could have my study hall too.
The only thing is, if you don't show up, if you don't take it tomorrow, you have to take it Friday. That's the only
Yeah.
thing. So you can't say come Monday and said,
Oh yeah, no, I understand. Could I actually come at like 7:30 and then just do an hour and go till 8:30, so I could have part of my study hall for my psychology
Oh.
class?
yeah, but I can't get you out of somebody's class.
Oh no, it's just my study hall.
Oh,
Yeah,
okay. So you're going to start at 7:30
7:30. Yes.
until 8:30.
8:30.
I can do that.
Perfect.
Thank you.
Thank you so much.
Thank you, Mr. Haney.
Bye.
Oh, also, I was gonna ask you, have you heard anything about what sciences they're offering?
Well, okay. We've had several discussions.
Uh-huh.
Right now, I think we are going to start an honors second year of biology, and Miss Founds would teach that. I asked them, if possible, to put that in a different time slot than the chemistry, because when we used to do it, people took both.
Yeah.
And so if you want to talk to Miss Plasma, but in the past, what always bothered us was Latin. Latin could only be taught once. But anyway, so that's the idea, and then they'll have the anatomy and physiology for the people who you want to take it a little easier. So. But they're going to maybe eventually, they could either have another teacher teach anatomy and physiology, because eventually Ms. Founds wants to give that up. And so I'm pretty certain we're doing an honors advanced biology.
Okay.
And anyway.
And that's with Miss Founds.
Mhm.
Okay.
And then we have the chemistry, the second year chemistry that we had every year.
Okay.
And then anatomy and physiology. So that, right now, that's what it is. Now, not we haven't looked into, maybe the following year, sorry. But the following year, the one AP class that you can do 1 hour a day for only have four, we only meet 4 days a week, might be environmental. But we were talked about, until they change it, AP chemistry, AP biology, you need 5 days a week all year.
Yeah.
And it would be a big push to try to do that here at Caldwell, I think.
Okay.
So right now, we voted, she actually, Ms. Plasma said, no, we're not gonna do that.
Yeah.
But we'll do a second year of biology, which I think would be good.
Okay.
So anyway,
stick
if you
with
tell Ms.
chemistry.
Plaza, say, if you happen to know, don't make it up. You happen to know that several people might want to take both advanced sciences and say,
Yeah.
and math, then I say, I'm giving up my foreign language, or I'm giving up my
Yeah.
band, or I'm giving up choir, or I'm, whatever you're giving up, not choir, but. So,
Okay.
I have no idea when they're gonna arrange it though, so.
All right. Thank you so much.
You're welcome. Oh, man, I didn't turn my video